Alrighty, good morning everybody, and welcome back to Abstract Algebra. So for today is we are going to continue our discussion of our follow-up to Lagrange's theorem, which I'll do a quick review of since it's been a while. Got my usual office hours this week. Today, Wednesday, the hour before class is from 2 to 3. Tomorrow from 10 to 11:30 and 1:30 to 2:30. I have posted a new homework set, homework 5. It will not be due for a little over a week. Just make sure you all have enough time to work on it. It won't be due until Wednesday next week, not Wednesday this week. And has some kind of questions on there about both isomorphisms and Lagrange's theorem / cosets, which are kind of both topics that didn't quite make it onto the that we talked about but haven't made it onto the exam yet. But you should be able to go through and look at those homeworks now. Just give you a sense of where I'm at grading wise. I finished grading homework 3. So I encourage you to go through and take a look at my comments. I'm going to try and get homework 4 graded by the end of this week. And that means I'll be working on exams next week if things go according to plan. And hopefully at some point I can get caught up. I encourage you to go look on Blackboard. Make sure you can see my comments that I've left you on assignments. I'm worried that you can't, and that would be terrible. So I left several of you some comments, and overall I think it went pretty well. I've also posted my solutions to homework 3, so you can kind of compare what you did with what I was kind of more looking for. Any questions or comments before we get started today? All right. So, several people one day were asked to test the following hypothesis, that all odd numbers greater than 1 are prime. The mathematician reasons, well, 3 is prime, 5 is prime, 7 is prime, 9 is not prime. Therefore, the hypothesis is false. The math grad student says 3 is prime, 5 is prime, 7 is prime, and by continuing the pattern, clearly all odd numbers greater than 1 must be prime. The physicist says 3 is prime, 5 is prime, 7 is prime, 9 is not prime, 11 is prime, and 13 is prime. Hence, 5 out of 6 experiments support the hypothesis. Clearly, it must be true. The computer science student, reading the output from the screen, says 3 is prime, 3 is prime, 3 is prime, 3 is prime. They need to work on their code. The biologist says 3 is prime, 5 is prime, 7 is prime. More research is needed. Psychologist claims 3 is prime, 5 is prime, 7 is prime, 9 is prime, but tries to suppress it. And finally, the politician says some numbers are prime, but the goal is to create a kinder, gentler society where all numbers are prime. Okay, so just do a quick recap. Last week we talked about cosets, which are these sets of the form. You take a subgroup H, and then you can form a coset by just taking everything in your subgroup H and multiplying it on the left or on the right by a fixed element. And so if H is a subgroup, then this set, AH, the set of all elements in H multiplied on the left by A, would be a left coset of H. H subgroup of some group G, A an element of G. And we used the idea of cosets and their properties last time to prove Lagrange's theorem, which is a theorem that says that if G is a finite group, doesn't have to be abelian, doesn't have to be cyclic, any finite group, and H is a subgroup of G, then the order of H has to divide the order of G. And also, the index of H and G is given as equal to the order of G divided by the order of H. So this thing we said was the index of H and G. Does anybody remember what the index of H and G refers to? That's what did my notes say?
Like unique cosets?
Yeah, Yeah, it's the number of cosets that H has in G. The number of left slash the number of right. Pick one, it'll be the same. But I'll say it's the number of distinct left cosets of H in. So basically, the number of cosets that H will have in a group is just always going to be equal to the order of the group divided by the order of H. Number of elements in G divided by number of elements in H. And Lagrange's theorem tells us this thing always has to come out to a positive integer, which will just be the index of H in G. And if you recall, last time I'd asked posed the question towards the end of class, does Lagrange's theorem work backwards? Meaning it's the converse true. So if K divides the order of G for some group G, must G have a subgroup of order K? So this is true for cyclic groups. The cyclic group has to have a unique subgroup of every order dividing the order of the group. But just because every subgroup of G has to have order dividing the order of the group doesn't necessarily mean that for every number dividing the order of the group, there has to be a subgroup of that order. And I think I made you all guess, and it turns out the answer is not necessarily. And that there are groups and numbers dividing the order of the group for which there is no subgroup of that order. And I think I had said what the example is, but didn't prove the example yet. I said on Friday, I meant last Wednesday. And as an example, we're going to take our group G to be A4, the alternating group on 4 elements. So the set of all even elements in S4. So all the even permutations on the set 1, 2, 3, 4, in other words. And our K is going to be 6. And then in this case, the order of G is the order of A4, which is 4 factorial over 2. 4 factorial is 24, divided by 2 is 12. So in this case, we have a K, which is 6, that divides the order of G. And I claim A4 has no subgroup of order 6. And I believe that's where we left off last time. I made this claim, but we haven't yet started to show that A4 cannot possibly have a subgroup of order 6. All right, pop quiz. What are some elements that are in A4? We have 12 elements in the group A4. I'd like to write them all out because it's going to be helpful to know what all the elements of A4 look like. I'll do the hard one. So what would be another even permutation in S4? So in other words, what could we could write as another element of A4? Next.
1, 3, 1, 2.
1, 3, 1, 2. Oh gosh, you're repeating things. Okay, so this.
Sorry, I meant like 1, 3 times 1, 2.
Like that?
Yes.
Yeah, the set of all products of 2 even permutations where they have nothing in common. That would certainly work. 1, 2, 1, 3. Okay, well that one would be equal to 1 maps to 2, 2 maps to 1 maps to 3, 3 maps to 1. Okay, so the 3 cycle, 1, 2, 3. Trying to make it difficult for me. So yeah, turns out all the 3 cycles in S4 are going to be in there. So we're going to have 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4, 1, 3, 2, 1, 4, 2, 1, 4, 3, 2, 4. And say 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, that'll be all of our 3 cycles. What else? That gives us 9 elements in A4, but we need 3 more. I think our other elements we can't necessarily write as a single cycle. So I'll give you one of them. One would just be, this is the product of 2 cycles, 1, 2, and 3, 4. So that's a product of an even number of 2 cycles.
1, 3, and 2, 4.
1, 3, 2, 4. And I think we need one more. So this one swaps 1 and 2 and swaps 3 and 4. This one swaps 1 and 3 and swaps 2 and 4.
One, 4, and then 2, 3.
1, 4, 2, 3. Yep, that should do it. So here's all our elements in A4. I claim if H is a subgroup of A4 with the order of H equal to 6, then all 3 cycles in A4 must be in H. So in other words, I claim we can show that if we were to have a subgroup of order 6 in A4, that each of our 3 cycles would have to be in that subgroup. And here is my proof. First of all, let's suppose A is an element in A4. Nah, let's not use A. Let's be fancy and say sigma. Let's suppose sigma is an element of A4 that is a 3 cycle. And that sigma is not an element of H. So we're going to do a proof by contradiction. We're going to assume that we have some 3 cycle sigma in A4 that's not an element of H, and then we're going to show that leads to a contradiction somewhere down the line. So we're going to suppose that we have some sigma that is not an element in H. So using what we know about cosets, what's going to be the rule? If sigma is not an element in H, what can we say about the left coset sigma times H in comparison to H? Are they going to be equal to each other?
No.
No, they are not. They can't be equal to each other from a property of, by lemma from the second page, property number 2. And in fact, by lemma number 5, sigma H and H have no elements in common. We know that sigma H can't generate the same coset as H because sigma itself is not an element in H. So sigma H and H have to be different cosets. And by lemma 5, that's the one we proved last Wednesday, since they're not the exact same coset, they can't have any elements in common. They're not the same coset, therefore, they're completely disjoint. All the elements in sigma H are not elements in H and vice versa. No common elements. And by lemma was this property? I don't have these memorized which numbers they are. But by lemma property number 7, we do know that the order of sigma H and the order of H have to be the same, which is 6. And so, what is that going to tell us then about sigma H H and the entire group A4. We know that sigma H and H both have order 6. We know they have no elements in common, and they're both going to be subsets of this group A4, where the order of A4 is 12. I claim that then has to tell us that everything in A4 has to be in one of these two cosets, because they both have 6 elements in them. There's no overlap, meaning they have to have 12 distinct elements, and the entire group only has 12 elements to begin with.
How do you deal with the identity element there? Because wouldn't it have to be in both groups?
The identity element's going to be in H, but not sigma H. Remember, sigma H, the coset, is not necessarily a subgroup. And in fact, by lemma property 9, the only coset of left coset of H that is a subgroup will be H itself. So sigma H is going to be a subset of the group G, but it's not going to be a subgroup, if that makes sense. Good question. So we know sigma H and H have no elements in common. They both have order 6. They're both within a group of order 12. Therefore, everything in the group has to be in one of those two cosets. Thus, A4 has to be equal to the union of H and sigma H. Meaning every element in A4 must be in H or sigma H, but not both. And here's going to be where a logical contradiction lies. It's going to turn out to be the case that we can show sigma squared is not in either of these two cosets, which would contradict this. And we're going to prove that by cases. So the first case I want to consider is the case where sigma squared is an element of H. So if sigma squared is an element in H, then sigma squared times sigma squared has to be an element in H as well, because sigma squared is in H, H is a subgroup, H has to have closure, meaning if you take anything in H and multiply it by itself, we should still end up back in H. Since H has closure. However, I claim if we take sigma squared times sigma squared, that's going to give us sigma to the 4th. And if sigma is a 3 cycle, what does sigma to the 4th have to be equal to?
Sigma.
Has to be equal to sigma again. Why? Because sigma cubed, if sigma is a 3 cycle, then sigma cubed has to be the identity. So multiplying again by sigma will give us sigma to the 4th, has to be sigma. But we have a contradiction here. We just showed that sigma squared times sigma squared is in H, but that means that sigma is in H, and we assume that sigma is not in H. This is going to contradict our claim that sigma was not in our subgroup H. So basically, this can't happen. Sigma squared cannot possibly be an element in H. Let me stop for just a second and see what questions y'all have so far. So we've basically shown that if sigma squared is an element in H, that would imply sigma has to be in H, which can't happen because we assume sigma from the start was not an element in H. So basically, this case is impossible. Our second case is one where sigma squared is in sigma H. I'm going to keep all of this up here still. For case 2. Well, if sigma squared can't be in H, then sigma squared would have to be in sigma H, right? Because everything in our group A4 has to be in one of these two cosets, H or sigma H. Sigma squared can't be in H, then sigma squared has to be in the other possibility. Check this out. If sigma squared is in sigma H, that then means, by definition, that sigma squared has to be equal to sigma times some little h, where little h has to be an element in big H. Because that's what it means for an element to be in sigma times big H. By definition, this coset right here is just the set of all things that can be written in the form sigma times some little element in H. But if that is the case, what does that tell us about sigma? If sigma squared is equal to sigma times little h, what does sigma have to be equal to? Let's see, someone other than Elaine, Nick, or Ryan. If sigma squared has to be equal to sigma times h, and we're working in a group, meaning we have cancellation, what must a single sigma be equal to? Okay?
H?
Yeah, we just cancel out a factor of sigma on both sides on the left. Multiply by sigma inverse on the left on both sides if you want. Well, that tells us then sigma has to be an element in H again contradicting our original claim sigma was not in H. Gadzooks. So we just showed that sigma squared can't possibly be an element in H. But sigma squared also can't be an element in sigma H. But everything in A4 has to be in one of those two cosets. Therefore, we have a contradiction, and our original sigma, our 3-cycle sigma, had to have been in H to begin with. So thus, sigma must have been in H. Hence, all 3 cycles in A4 are in H. Because we took sigma to be an arbitrary 3-cycle in A4, and we showed that if sigma, that arbitrary 3-cycle, is not in H, then we arrive at some trouble, and that sigma squared both can't be in H and also can't not be in H. So basically saying sigma had to have been in H, because if sigma was not in H, we have a logical contradiction that occurs. So that tells us all 3 cycles are in our subgroup H of order 6, right? So in other words, all 1, 2, 3, 4, 5, 6, 7, 8, all 8 of our 3 cycles have to be in our subgroup of order 6. Lane, you taking offense to that?
That's terrible.
Why is that terrible?
Because then the order would be 8, but it would have to be more than 8 because you have to put the identity in the subgroup.
Oh my gosh, then the order of H would have to be at least, have to be at least 9, because we have to have the identity and all 8 things, and H couldn't be a subgroup of order 6 to begin with. But since there are 8 3 cycles in H, or not in H, in A4, this implies the order of H has to be at least 8, contradicting our claim that the order of H is 6. So in other words, if we have a subgroup of order 6, then it has to contain all the 3 cycles, and therefore it has to have order at least 8, meaning it can't possibly have had order 6. So in other words, A4 cannot possibly have a subgroup of order 6. Thus, A4 has no subgroup of order 6. Thus A4 has no subgroup of order 6, despite the fact that 6 divides the order of A4. Yeah, right?
Could we have made this conclusion only using lemma 9? It says AH is a subgroup of G if and only if A is a member of H.
Let me. H is a subgroup of G if and only if A is an element of H.
Yeah,
Sure.
G equals H.
If H is equal to G?
So, sorry. I'm just thinking that you would have to assume sigma is a member of H to even get a subgroup. And then since you need a subgroup of order 6, then you would have to assume that sigma is in H to begin with.
Right. If sure, but just because H is a subgroup of G does not mean that every element in G times H has to be equal to H in order to have a subgroup of order 6. It's totally possible. There are plenty of groups of order 12 that do have subgroups of order 6. Z mod 12Z is a cyclic group, and so it has to have a subgroup of order 6. And then it's just the case that every element in G is either in H, or it's in the coset of G, or it's in the coset that's not equal to H in that case, which would be totally fine. Here, we have to kind of go through all this work and arrive at a contradiction by showing that if we have a subgroup of order 6, then it has to have at least order 8, which makes no sense at all. So, and that's specific to knowing what the elements in A4 look like. The reason why I wrote all this out is I wanted to make it clear that we have way too many 3 cycles to possibly be in a subgroup of order 6. Does that make sense? I'm glad you stopped and asked me that. So, turns out this is the smallest counterexample, I believe, to Lagrange's theorem, to the converse to Lagrange's theorem. Turns out that every subgroup of order 11 and less will always have a subgroup of any order dividing the order of the group. So here we have a group of order 12 with no subgroup of order 6, but that can't happen unless your group has at least order 12. If your group has order 1 through 11, then any number dividing the order of your group will have to have a subgroup of that order. You have to go all the way up to 12 in order to find a counterexample here. Any questions or comments about that? So one of the things I talked about kind of in passing in the last packet was I said that we talked about how many subgroups there are of every order, and I said something like 99% of all subgroups, or 99% of all groups of order less than 2,000 have order 1,024 specifically. I also mentioned that if your group has some prime order, there's only a single group of each prime order, meaning if you have a subgroup of order P, or if you have 2 groups of order P, they're always going to be isomorphic to each other. I mean, there are no, every group of order P has to mathematically be the same as long as P is prime. So what I'd like to spend the rest of class on today is actually proving that claim and show that any two groups that have the same prime order have to be isomorphic to each other. Because that's something we can do without too much trouble using the Lagrange theorem. So let's see if we can do that. Any more questions about this before I erase it? So one corollary to Lagrange's theorem we can start off with is this theorem, which says if G is a group with the order of G equal to P for some prime P, then G has to be cyclic. That all groups with prime order have to be cyclic, have to be able to be generated by a single element. This is something that's certainly not true for groups in general. We've seen plenty of examples so far of groups that are not cyclic, even though they have finite order, like the dihedral groups, the symmetric groups. All of these are groups that have finite order but are not cyclic. And so what this theorem claims, though, is that if the order of your group is some prime number, 2, 3, 5, 7, 11, 13, etc. Hey, how about that? My joke of the day actually fit in. That was unintentional. If you have a group whose order is a prime number, then it has to be a cyclic group. So let's see if we can prove that using Lagrange's theorem. So let's suppose that we have a group that has prime order, so that the order of G is P for some prime P. And I want to let A be an element in G such that A is not the identity element. So by Lagrange's theorem, we know something about the order of the group generated by A, namely that it has to divide the order of G, which is P, right? So the group generated by A has to have order dividing the order of G, because the group generated by A has to be a subgroup of G, and the order of any subgroup divides the order of the whole group. So then, if you look at this, the order of the group generated by A is a factor of P. And since P is prime, what does that tell us that the order of the group generated by A could be? If it divides the prime number P, what are the possibilities for what this order could be?
1 or P.
It has to be 1 or P. So order of this group equals 1 or P, since P is prime. Here we're using the fact that P is prime, meaning P has no positive integer factors other than 1 and P. Don't try and tell me that the order of that group could be -1 or -P, because that makes no sense. So we know that the order of the group generated by A has to be either 1 or P. Can it be 1? Meaning, is it okay for the group generated by A to only have a single element in it?
No, because that would have to mean A is the identity, and we said it's not.
Yeah, this is why I established A is not the identity element, because if A is not the identity element, then the group generated by A has to have more than one element in it. It has to have, at the very least, the identity element and A itself. So since A is not equal to the identity, A does not generate a group of order 1, and so A has to generate a group of order P. But wait, the entire group has order P. So what does that tell us about the relationship between A and our group? If the group generated by A has the same order as the entire group, right?
It's a generator.
Yeah, A has to generate the entire group. And group generated by A equals G, so G is cyclic. So in other words, you pick any non-identity, you have a group of order P, you pick any non-identity element, it has to generate a subgroup of order dividing the order of the whole group. Well, if the order of the whole group is prime, then that means you have to have a subgroup of either just order 1 or the order equal to the whole group. And therefore, as long as you're not looking at the identity element, which will generate a subgroup of order 1, you have to have us be generating a subgroup of order equal to the order of the entire group. And the only way that A can generate a group of the same order as G is if A does in fact generate G, which would make G a cyclic group. So there are so in other words, there's no groups of order 2, 3, 5, 7, 11, etc. that are not cyclic. They all have to be cyclic. Questions or comments? Here's the punchline. Not only do they have to be cyclic, we haven't shown this yet, but I also claim that if you have a group of order P, that means it's cyclic, and I'm going to also show that if you have a cyclic group of order N, it has to be isomorphic to Z mod NZ. In other words, Z mod NZ is the only mathematically unique group of order N that happens to be cyclic. So let's see if we can prove that. This is another theorem that says if G is a cyclic group with the order of G equal to some number N, then G has to be isomorphic to Z mod NZ. And notice that in this theorem, N does not necessarily have to be prime. This is true for any cyclic group of finite order N. N could be prime or composite. Either way, if the order of G is equal to N, and if G is cyclic, G has to be isomorphic to Z mod NZ. Let's prove this. Let's let G be a cyclic group. I'll say it's generated by A. And suppose G has N elements. That G has order N, in other words. And we want to show that G is isomorphic to Z mod NZ. How do we prove two groups are isomorphic? What does that necessarily mean about two groups if we say that they're isomorphic? Nick?
There has to exist some homomorphism that is one to one and onto from one to the other.
Yeah, we have to be, two groups are isomorphic. By definition, that means we can have there exists an isomorphism from one group to another. A function from one group to the other that is a homomorphism that's one-to-one and that's onto. So what I'm going to do is I'm just going to find an isomorphism from G to Z mod NZ and then show that function is in fact an isomorphism. We're going to define a function called phi from G to Z mod NZ. And the way I want to define this function is I'm going to take phi of a to the k power. I'm going to map it to k mod n. So in other words, we know that G is a cyclic group, meaning everything in G has to be some power of A. Well, what I want to do is I'm going to define a map from the group generated by A to Z mod NZ, and my goal is just, and the way we're going to define this is whatever power of K, whatever power of A we're taking, A to the K, we just map that element to its power, to K in other words, where phi of A to the K is going to be equal to K mod N. So in other words, we'd say phi of A itself would be 1 mod N. Phi of A squared would be 2 mod N. What would phi of the identity element be? If the E is the identity element in our group G. Alright. I would say it's going to be phi of A to the 0, which would be 0 mod N. I wouldn't say N specifically, because when we talk about Z mod NC, we really mean like just the integers 0 through N minus 1. Technically, you could say, oh, 0 mod N is equal to N mod N. You could do that, but I want to define it in a way that only maps to the... I want to do it in a way in which the only unique elements of Z mod NZ we're going to say to be the integer 0 through N minus 1. So you wouldn't be wrong to say that's equal to N, but I don't like it. That's the way our function is going to work. By the way, what would phi of A inverse be? I mean, there's no point hiding from true mathematical justice. Yes?
Would it be N minus 1 mod N?
It would be negative 1 mod N, which would in fact be equal to N minus 1 mod N. So A inverse is going to map to N minus 1, etc. So there's our map. I claim this is an isomorphism. And to show this is an isomorphism, you need to check the 3 things. We need to show phi is a homomorphism, phi is 1-to-1, and phi is onto. Oh, let's see. Callie, which one would you like to show first? Homomorphism, 1-to-1, or onto? It's a good place to start. Yeah, let's show phi is a homomorphism. By the way, that's what I was going to do first, regardless of what you said. So let's see. I claim phi is an isomorphism. And here's our proof. Start by showing phi is a homomorphism. So recall, phi being a homomorphism means we need to show that phi of xy has to be equal to phi of x, phi of y, where we replace multiplication with whatever our group operation is here. So let's see. In Z mod NZ, our group operation is addition mod n. And the cyclic group G, x, y is just going to be we multiply them together. So now we can say, given any, let's say a to the n, or no, not n. Let's say a to the k and a to the j in G. Here G is cyclic, so any element in G has to be a power of a. I claim phi of a to the k times a to the j should be equal to phi of a to the k plus phi of a to the j. So let's see if we can show that. Well, a to the k times a to the j. We multiply that out first before applying the map phi. That's going to be a to the k plus j. If k copies of j and j, if you have k copies of a and j copies of a, you multiply them all together, you're just going to get k plus j copies of a. what would phi of a to the k plus j be? Alright.
K plus J mod n.
K plus j mod n. Glad you included the mod in there, because you just said k plus j, I was going to say wrong. Because it could be that k and j are too big. If k plus j is greater than n, then phi of a to the k plus j is not going to be k plus j. It's going to just be whatever you get when you mod out by n. Which, using the associativity of addition and mod n, I claim is going to be k mod n plus j mod n, which will be phi of a to the k plus phi of a to the j. Neato mosquito, we have a homomorphism. Because if we apply the group operation in G and then apply the map phi, we're going to get the same thing every time as if we applied phi first to our two things in G and then did the group operation in Z mod n Z to those two elements. Let's put the little n down there to make it clear we're doing addition mod n. Okay, so phi's homomorphism. Got two more things to show. That phi is 1-to-1 and phi is onto. Becca, which one would you like to do next?
1-to-1.
Ooh, the harder one, okay. So now we want to suppose that phi of a to the k is equal to phi of a to the j, and we have to show that that would imply a to the k and a to the j are equal to each other. That if they map to the same thing under phi, they have to have been the same thing to start with. Well, if phi of a to the k is phi of a to the j, then I claim that says k mod n has to be equal to j mod n by definition, which in turn is going to imply k minus j mod n is 0. If k minus j mod n is 0, what does that actually tell us about k minus j as an integer? What relationship does k minus j have to have with the integer n if when we take k minus j and mod out by n, we get 0? Here?
Not equal.
Or it could equal n, but it could also, doesn't have to equal n itself necessarily.
Or multiple event.
It has to be a multiple event, exactly. So then k minus j has to be, I don't know, Sn for some integer s. Well, if that's the case, if k minus j is a multiple of n, then if we take a to the k minus j, that's going to give us a to the power of Sn, which is the same as a to the n raised to the s. But what's a to the n? If A is a generator of G and G is a group of order n. Right? Has to be the identity. EGADS. So that tells us A to the k minus j has to be the identity element, which in turn will then tell us A to the k has to be A to the j, because we could just multiply both sides of this equation by A to the j. And we get a to the k equals a to the j. Awesome possum, lemons blossom. We now know that phi is a 1-to-1 function. Gabe, what's the last thing we need to show about phi to get the phi's isomorphism?
I forget.
Oh no! Is that phone a friend?
Yes.
Okay, phone a friend.
Friends.
We need to show this onto. Yeah. That's a function.
So Gabe, what's your point? Oh, all right, we don't have much time for this. Let's do this. Alright, we also need to show phi is onto, which is actually pretty quick. Alright, it's so quick I'll just do it right here. Alright, we're going to let B be an element in Z mod NZ. Then B is equal to phi of A to the B if we're done. Any element in Z mod NZ just has to be equal to, by definition, phi of A to that whatever power that is. Alright, phi is an homomorphism, phi is onto, phi is 1 to 1, therefore phi is an isomorphism from G to Z mod NZ, therefore G is isomorphic to Z mod NZ. So what have we shown? We've shown that every group of prime order has to be cyclic, and any cyclic group has to be isomorphic to Z mod NZ. Any finite cyclic group has to be isomorphic to Z mod NZ. So we're going to have one more page, but it's going to take us like 5 minutes next class, basically to sum up by saying, if G has prime order, then it has to be isomorphic to Z mod PZ specifically. And thus, all groups of the same prime order have to be isomorphic. All right, next time, we're going to start talking about direct products, which is going to give us a way to take two groups and multiply them together to make a bigger group. And then after that, we're going to have the more fun one, which is we're going to talk about how you can take two groups and divide one group by the other group to get a smaller group. Have a good day, everybody. I'll see y'all on Wednesday.